The next speaker is Dezső Horváth, and tell me if I mispronounced your name.
It's okay.
He is honorary professor at the University of Dezső, professor emeritus at the Wigner Research Center in Budapest. Professor Horváth is an experimental particle physicist who has participated in collaborations with various particle accelerators in Russia, Canada, the US, Switzerland, and CERN. That's that big facility that Professor Hoof was mentioning. He's currently the manager of joint research groups Budapest and Debrecen to test matter-antimatter equivalence using slow antiprotons. And he is involved in a search for new physics in proton-proton collisions at the Large Hadron Collider. That's at CERN. His plenary lecture is titled Hunting the Higgs-boson. Is it found at LHC?
I have the microphone, thanks.
You have the microphone,
yes,
great.
A clip-on. Can you hear me? Doesn't work? I need this one. Yes, okay. Okay, so I use both. Very good. So it's a great honor for me to be able to speak about our CERN experiments. It is already the third Symmetry Festival where I am speaking about it. Up to now, it was just searches. We experimentally searched for symmetry violations mostly at various points of particle physics. This is the first time I can speak about an observation, a discovery. So my title has a question, and the answer in short is yes, very probably. So oops. I try to make this work. Yes, it does. So this is the outline of my talk. I am very lucky that Professor Delft introduced the Higgs boson. I don't have to speak about it, its introduction. So I shall tell about its search and observation at LHC. The basic question is whether what we found is really the standard model Higgs boson or not. So this is now the main branch of investigation now. Then I shall speak a few words about the search for supersymmetry at the LHC, and then finally our plans and hopes. Now, I am a member of the CMS collaboration. Now, these high-energy physics collaborations are very strict. I can report results only which are approved by the whole collaboration, and I have to show the source of my information. So I shall use these two papers by CMS, published, and a preliminary paper, and two similar papers from Atlas. So we heard the standard model from Professor Delft. Actually, I shall use the word Higgs field and Higgs boson, but the spontaneous symmetry breaking in principle should have all these names, who published it in 1963, 1964. So it's practically adds a four-component symmetry breaking field to the vacuum, and then we separate out of these three local symmetries, we ruin two, and then separate the electromagnetics from it, which produces a zero mass photon, which is good, and then the rest of the four components of the Higgs field gives masses to the weak gauge bosons, the mediators of the weak interaction, and the fourth degree of freedom becomes a heavy scalar boson, which is the Higgs boson. Now, we heard all this from Professor Delft. Everything was clarified, studied in detail, and so on in the last 40 years, except the Higgs boson, which was observed probably, very probably, as I have to say, last year. So I have to emphasize that the standard model, the theory of particle physics, of which Professor 't Hooft spoke, very well describes all experimental data observed so far. It is just amazing. We were building one accelerator after the other, constructing one experiment after the other, and we couldn't find anything which would significantly deviate from the predictions of the standard model. For instance, among these basic parameters, only one is different by more than two uncertainties from the theory. Two are between 1 and 2 uncertainty, and all the rest are within 1 uncertainty, which is exactly according to the statistical laws. As we heard, the Higgs boson, this picture was explained by Professor 't Hooft. The standard model says that the Higgs boson must exist. The standard model just doesn't work without it. So we believed that the Higgs boson exists even when we couldn't find it for 40 years. Now, there are many jokes of the Higgs boson in the press. I like these two. Before the discovery, this was the most important one. The Higgs boson walks into a bar, and the bartender says, "Watch out, there were some guys looking for you." I must say there were 10,000 physicists looking for the Higgs boson. The other one is even better. The Higgs boson walks into a church, the priest says, "Your kind is not welcome here." And the boson replies, "But without me, how can you have mass?" Mass in 3 senses. Mass in the sense of mass of people, the mass of the elementary particle, and also the religious ceremony is mass in English. So where is the Higgs boson? There is a very nice paper of Peter Higgs published in 2002, entitled "My Life as a Boson, the Story of the Higgs." And he says there that it was in 1972 that my life as a boson really began. Now, what I shall speak about is experiments at CERN. CERN, as you probably know, is the largest laboratory on Earth. It has 13,000 people working in it. And it has a very complicated accelerator structure, and the large one is the Large Hadron Collider, and I shall mention the results of 2 experiments, CMS and Atlas. These are the 2 large experiments with 4,000 people working for it each. So this accelerator complex is quite complicated. The protons are passed over from one accelerator to the other until they could be accelerated to the 8 TeV of last year and 13 or 14 TeV starting from 2015. Just for curiosity, I tell you that the CERN neutrinos to Gran Sasso is also part of CERN. This shoots neutrinos through the Earth to the south of Rome, where this Gran Sasso underground laboratory is located, and there was the famous opera experiment which taught that they find faster than light neutrinos, which proved to be wrong afterwards. So anyways, this is an aerial photograph of CERN where the 27-kilometer long circumference accelerator, which sits 100 meters underground, is also drawn. This is the Geneva International Airport, and that triangle is the CERN main laboratory where 13,000 people work. So these are the Large Hadron Collider is a circular collider, circular machine where in 2 directions protons are kept in orbit by 1,232 superconducting magnets, These are some of them which are waiting for building in. Each of them are 50-meter long, 35-ton weight, and they keep the magnets at 1.9 Kelvin. This is how LHC, the machine itself, looks like now as it is built. You can see that it curves. It's circular. Now, the measure of the performance of a collider machine is called luminosity. This is practically the collision yield, and it corresponds to the flux.
You need to speak into the microphone.
Into the microphone. Ah, okay. It's better this way. Yes. So it's not symmetric. It's very asymmetric. Yes. So, anyways, the luminosity corresponds to the flux at fixed target accelerators, and if we have the luminosity of, for example, in the case of LHC, in proton-proton collisions, when we multiply it by the cross-section, which is the probability of a reaction, and the efficiency of detection, then we get the number of events what we can expect. Now, LHC had an amazing performance since its start in 2009. Oops, I didn't want to jump yet. In 2010, in the first full year of operation, it collected 0.04 inverse femtobarns, whatever it means, it doesn't matter. In the next year, it collected at the same energy, at 7 TeV, 5.6, which was 140 times more. And in 2012, last year, it increased the energy to 8 TeV and collected another factor of 4 more luminosity, more information. Now, I feel lucky because the Netherlands is in Atlas and Hungary, where I am from, is in CMS. So, of course, Professor 't Hooft mentioned Atlas, and I shall base my talk on CMS. CMS, compact muon solenoid, it is called. It is compact because its volume is 10 times smaller than that of Atlas, but its weight is 3 times more. It has twice as much steel as the Eiffel Tower in Paris. And so it's a 14,000-ton digital camera, and it produced last year 20 million pictures per second, and we had to choose 400 out of it. So we had to use a very, very intelligent filter to choose the registered data, because we could register only about 400 per sec. The CMS collaboration last year had 3,275 physicists from 179 institutions of 41 countries. 1/3 of the physicists were students, plus 790 engineers. By far, the largest participation is coming from the United States, next Italy, then Germany and Russia. It's a huge joint effort. Just imagine that 3,000 people worked on it for 20 years to build it and make it work. So how the Higgs boson is formed in proton-proton collisions at the LHC. Here in this picture, you see on the horizontal axis the assumed mass of the Higgs boson, and the vertical axis is the probability of reaction. Now, you can see that the green line, which is hardly seen on the picture, is by far the most prolific reaction, the so-called gluon fusion reaction, which could produce the Higgs boson. The proton has a very complicated structure. In addition to the 3 quarks, it has lots and lots of gluons, which are the force carriers between the quarks. So that's why gluon-gluon collision is by far the largest probability when you collide 2 protons. Then the second largest is the so-called vector boson fusion, when a two quarks, so a quark and an antiquark, collide, and they scatter off and produce a Higgs boson in the meantime. So we were looking for these two reactions, basically. Now, how the Higgs boson can be detected? Of course, it decays immediately. So at lower masses, so below 120 megaelectron volts, MeV masses, the dominant reaction is the two heavy quarks, a B quark and a B antiquark. At high masses, above 150 GeV, it is the 2W decay, so two W's, and then the W's decay further in various ways. Now, of course, as a result of that, the previous CERN accelerator lab excluded the possibility of having a Higgs boson below this mass, and the high masses were very fast excluded by the LHC experiments. And as time grew, this region, which was allowed to the Higgs boson according to the experiment, was shorter and shorter. And in March 2012, where we finished analyzing the 2011 data, we confined already to this yellow region the possible mass of the Higgs boson. Now, we couldn't exclude this part because we already had an excess observed 2-3 times the experimental uncertainty, which we call sigma experimental uncertainty, at around 125 GeV. So we felt last spring that the Higgs boson is condemned to be discovered in 2012. Now, you can see that in this critical region, there are many different possible reactions are for the decay of the Higgs boson. Now, funnily enough, what can be really identified are the two, apparently the two lowest probability reactions, the gamma-gamma decay, so decay of two photons, and the ZZ decay with 4 leptons, 4 charged leptons. And so both big experiments optimized the photon detection, which we called electromagnetic colorimeter, for studying this decay. So, for instance, the electromagnetic colorimeter of CMS consists of 75,000 lead tungstate single crystals. It took 10 years to produce them. So this is an event which could be a Higgs boson decaying to 2 photons. We call it candidate because, of course, we don't know exactly where it is coming from, but it could be from a Higgs boson. You can see here that the 2 protons come in this way into the detector. They collide in the middle, and then they produce a lot of charged particles. Each yellow line is a charged particle curving in the magnetic field of the detector, and there are 2 very high energy photons, and this is how we identify that it could be from a Higgs boson. So on the 4th of July last year, the 2 big experiments, ATLAS and CMS, announced that at both LHC collision energy, 7 and 8 TeV, in the 2 decay channels, which I mentioned already, at the same invariant mass, as we call it. So the invariant mass means that we calculate that what mass should have the particle which decayed into the given decay products. Around 126 G, we see a new boson at a convincing statistical significance of 5 sigma confidence level each. There is a general agreement in high energy physics. We cannot say that we see something unless it steps out to 5 experimental uncertainties from the background. So it is obviously a boson, and it has, because it can decay to 2 photons, it has either 0 or 2 spin. Fortunately, spin was explained by Professor 't Hooft. So, nevertheless, we announced there that we have to show that it is really a Higgs boson, and it is really the standard model Higgs boson. Now, the mass of the Higgs boson, of the boson, decaying boson from 2 photons, can be well identified using this vector boson fusion process, because we have the 2 hard photons and we have the 2 quarks scattered off, these 2, the quark and antiquark, and these produce hadron jets, as we call it, showers of particles. So the fact that the LHC has an enormous luminosity means that each event has many, as an average, 20 proton-proton collisions. We have very big bunches of protons colliding, so not only 1, but usually 20 collisions happen every time in every event. This is the record we have in CMS, 78 identified proton-proton collisions in the same event. This, of course, makes the data-taking speed high and life very hard for the analysis. Now, this is the discovery, one of the discovery pictures. So what we have here is the assumed Higgs mass, actually the gamma-gamma invariant mass on the horizontal axis between 110 and 150 GeV. And on the vertical axis, we have the number of observed events. And you can see this peak, which steps out by practically, when we add together, by 5 sigma from the background. Now, the background is very well described by theory. This is one of those figures which are amazing, which show how well the standard model describes the experimental data. And it is, you can read it, that it is about 125 GeV. Of course, Atlas had exactly the same result. In high energy physics, we don't believe anything until 2 independent experiments don't show it at the same place. So this is very important, that Atlas had exactly the same result at exactly the same Higgs particle mass. Now, this is the other reaction, the charge lepton decay of the possible decay of the Higgs boson. These are the experimental data with the experimental uncertainties, and this red curve is the standard model prediction. Now, let me interrupt this talk for a sec, and I want to show you something, how this we achieved actually. Oops, this is not good. So this shows how the data were collected in time. So we had the run starting in 2010. Let's start it again. Started in 2010, and this is how the information was gradually collected. We have the standard model prediction for the 126 GeV Higgs boson in red here. And you can see in the beginning, we have just a slight excess. And it is growing and growing and growing. And it is quite convincing by the time the LHC stopped in December 2012. And of course, it all agreed with the prediction. Not of course, but unfortunately, it always agrees with the prediction of the standard model. Now let's return to this. So, the real result, I must say, is a little bit more complicated than, because somehow we want to add together all the possible information into one picture, and that's the so-called p-value, p-distribution. I must say that the physicists love it and the statisticians hate it. This is the probability, this is the inverted probability. This is the probability that random fluctuations of the measured background could give what we see, the excess. Now, you can see, this is the CMS result. So, you can see that at the 4th of July talk, we had, if we added together the gamma and ZZ event, we had exactly 5 sigma. So this is why we could say that we see something new. If we added WW to it, although it had no peak, the WW curve, but it still increased the significance to 5.51 sigma. Funnily enough, when we added everything together, it decreased the significance because we added more background than signal. Now, Atlas got the same result. Gamma and ZZ was 5 sigma. But when they added WW, then it increased to 6 sigma. But this is within uncertainty, of course, within statistics. Now, by November, this significance was increased to 6.9 sigma. Now, if you look at this figure, this is again the p-value, this probability. This dotted line, dashed line, is the standard model exception for a given mass of the Higgs boson. And you can see at 126 GeV, we get close to it. Otherwise, the experiment is very, very far away. So this shows, actually, this on the right side, we have exactly the same thing, but increased in scale. So you can see that there is no other Higgs boson. We cannot hope, based on this information, to get another Higgs boson using these experiments. Now, of course, the best two masses what we have for the new boson is different. They are different from the two measurements. Of course, why should they be exactly the same? But they are the same within error, and the average is 125.7. It has a statistical uncertainty of 0.3 GeV and the same number for the systematic. The statistical uncertainty comes from the detected number of events, and the systematic uncertainty comes from model assumptions, from detector uncertainties, calibration, and so on. Now, in March this year, CMS already established that the data favor really the standard model Higgs boson spin and parity. So it prefers the zero spin and positive parity for the data, for the new boson. Now, the most sensitive test is the test whether the various particular decay channels, for the various particular decay channels, the prediction and the experiment agrees. And you can see on these figures that in all cases, the best fit, the detected probability divided by the probability of the reaction predicted by the standard model. So this is the observed per predicted. They are very close to 1, and the experiment is consistent with itself. That means that the various channels produce within uncertainty the same kind of data. Atlas had very similar results. Now, for a long time, we hoped to see some deviation from the standard model, but we couldn't. This is actually very, very sad, because that means no new physics behind this experiment at the moment. Now, the mass and signal strength, Atlas and CMS has exactly the same mass. Look, 125.5, 125.7, and all within uncertainties. CMS got 20% less signal strength than what is predicted by the standard model, but unfortunately Atlas got 40% more, to the average is very close to 1 again. So all agree with, unfortunately, with the standard model. Now, what does this mean? Professor Toft already mentioned that this 126 has a very peculiar mass for the Higgs boson. Now, I just quote one paper which was published very soon after the appearance of the first results, which says that this 126 GeV for the Higgs, this is on the horizontal axis, it is the assumed Higgs mass. On the vertical axis is the top mass of the top quark. That is a very sensitive, that's the heaviest quark, and its mass is a very, very sensitive parameter of the standard model. And you can see that this, what we found, this blue line at LHC is actually very close to the stability border of the standard model. This green part is the stable standard model region, which means that the standard model works up to the very high so-called Planck energy. This orange one means a metastable region. That means that somewhere below the standard model may break down and new physics could appear. And of course, the red region that means that the electroweak vacuum is unstable. That is out. So, and you can see that we need a lot of further studies to establish where exactly the Higgs boson appears on this figure. Now, what is next? There are some people who ask us experimentalists, what will you do? You built an accelerator, you found the Higgs boson, what next? Now, Professor Toft explained supersymmetry, so as I mentioned, the standard model is very good to describe the experimental data, but it has quite a few inherent theoretical problems, and I won't go into it, actually, but there are lots of theoretical problems, and one of them, I just quote one of them, there's the dark matter of the universe, which is obviously, which has 23% of the mass, gravitational mass of the universe, and obviously it is some kind of particle. It has to be because it moves and gets together, it has a gravitational field, but it is out of the standard model. Now, all these problems are solved in the supersymmetry theory if supersymmetry exists. We used to joke that 50% of the supersymmetry world is already discovered. Of course, that's the ordinary matter, especially now that we think we found the Higgs boson. Now, one of the great things about supersymmetry, even the minimal supersymmetric standard model, is that it helps to unify the interactions. So the interaction, the strength of the 3 gauge interactions don't meet in the case of the standard model, and they meet very nicely at 10 to the 16, 10 to the 18 GeV using supersymmetry. There are, of course, many, many alternative models, and we shall hear of one of them in the next talk by Professor Darvas, actually. So how do we look for supersymmetry? The supersymmetric particles should be produced in pairs and decay to other SUSY particles. So that means that the last one should just go away. We cannot observe it. So that, first of all, that lightest supersymmetric particle is an excellent candidate to explain, to constitute the dark matter of the universe, and it helps us to observe it because it means missing energy, missing momentum in the experiment. Also, even the minimal supersymmetric standard model assumes 2 Higgs doublets, so that means 5 Higgs bosons, yes? Because 2 doublets means 8 degrees of freedom, and 3 produce the masses for the 3 heavy bosons, and there are 5 Higgs bosons. 3 neutral and 2 charged Higgs bosons are produced. So, unfortunately, the simplest supersymmetric models are already excluded by the LHC data. So, okay, those are very primitive because even the minimal supersymmetric standard model has 105 parameters, and in the simplest version, this is reduced to 4, but this is out. I mean, these very simple models are probably excluded. But even if supersymmetry is valid, the minimal models may not be. So what we have to do is search for more Higgs bosons and check for simplified phenomenology. So what does it mean? Simplified model. We assume very simple reactions and try to fit them using the standard model only. So look for deviations from the standard model. Once we find it, then we can think about how to explain them. So far we couldn't find, Professor Toth has put the atlas result of exclusion almost 1 to 1 TeV of the various possible supersymmetric particles. CMS has, of course, the same result. So this is an example of such exclusion with simplified models. We have 2 protons colliding. We assume that two gluinos are produced. These are the supersymmetric partners of the gluons, and each of them decays to 2 top quarks plus an invisible particle. And the mass of these gluinos can be excluded using such figures, such diagrams, which help the theoreticians to confine their theories. So anyway, so now I finish. Yes. Conclusion. So we very pardon. We very probably observed the standard model Higgs boson, or less probably a Higgs boson of a more general model. Actually, it has to be a Higgs boson, what we see. But it could be another model's neutral Higgs boson. Let us hope for some deviation from the standard model. Unfortunately, we are not seen yet. The simplest SUSY supersymmetric models do not seem to be supported by experimental data, and not only the LHC, there are lots and lots of experimental data. We started simplified approaches for looking for new physics, and it may help to find new characteristic reactions, and if found, we try to identify the new observation with possible models. The basic conclusion is that we have to adjust theory to data and not the other way around. For years, for many, many years, we tried to assume some kind of model and then checked it using the experiment. Now we turned it around. And finally, that's another joke, experimentally asked the theorist, what happens to you if we exclude the whole SUSY in 2012? And the theorist says we are far from that. The minimal model is not the whole SUSY, and anyways, we are not doing that only. Thank you for your attention. But so, questions?
I have a question.
Yes?
I'm curious if there are particular extensions to the standard model which CMS is more sensitive to than Atlas or Atlas and CMS, or are you both sensitive to more or less the same kinds of
Yeah, actually it's very funny. You see, Atlas and CMS are very different, and we get exactly the same result in practically everything. You could see differences in the Higgs probability, what we found, but everything everything agrees with each other. And anyways, learning from the very bitter experience at the Tevatron experiments, where the two large experiments, D0 and CDF, were fighting with each other all the time. So whenever one of them announced that they found something new, the other one tried to negate it and always succeeded. So this is something which we don't want to do at the LHC. So there is an agreement if Atlas or CMS feels that they discovered something new, the agreement is that the spokesman goes to the Director General of CERN, tells him about it, and the Director General invites the spokesman of the other experiments and leaves 2 weeks for them to check it. We have the same kind of data. So it's just an idea of the analysis which could lead to a new discovery, actually. So this is a very wise thing. So that's why, for example, when CMS and Atlas published his discovery, it was published in the same Physics Letters B paper issue. And these publications look very nice, actually, because 16 pages of text is followed by 17 pages of the list of the authors, because there are 3,000 authors in each paper, actually. Questions? No more. Yes? Yeah? Yes?
I was wondering, what's the laboratory energy that's using the 70? Oh, the 70 eV is the center mass, center momentum energy.
Yes.
What was the lab? I can't do the computation quickly.
Yes. So in 2010 and 11, 70 eV was the total collision energy of the proton. So that means 3.5 TeV per proton. In 2012, we managed, the accelerator people managed to increase this to 8 TeV. Originally, the design was 14 TeV collision energy, but when in 2008, just after the start of LHC, the accelerator people started to increase the magnetic current corresponding to, this stopped work, no. Corresponding to 14 TeV, so 7 TeV, both beams, then there was a disaster. One of the magnets broke down, and the accelerator complex had to be stopped for 1.5 years, and 53 magnets had to be brought up and repaired. So that's why the LHC afterwards started exactly half the energy, the design energy, but we hope very much that in 2015, when it will restart, then it will have already 13 we want to have 14 TeV. The accelerator people insist on 13 only, so probably they will win, I bet. Yes.
Thank you very much.